Imagine you build an AI chatbot for your company, and a customer asks, "What's the refund policy for enterprise plans?" The AI replies with a generic answer about typical software refund policies. It misses the actual policy, a 60-day prorated window, because that detail is buried in a 200-page internal company wiki. The model cannot know what it was not trained on. The traditional fix is fine-tuning, training the AI on your internal documents. But that process can cost thousands in compute power. The model becomes stale the moment a document changes, and there is no way to trace exactly which source the AI used to generate its answer. Instead of permanently altering the model, we can provide it with temporary external context. This is Retrieval-Augmented Generation, or RAG. It leaves the original model untouched while allowing it to answer questions using your specific private data. Every RAG pipeline follows 4 steps. First, we take the user's query. Second, we retrieve relevant passages from your document store. Third, we augment the prompt by pasting those passages in. Finally, we let the AI generate an answer using that context. This approach grounds the AI in verifiable facts. Because the model refers to specific documents to find its answers, it is cheaper to maintain, easier to audit, and updated in minutes. Step 1 is preparing the data. If we feed an entire 200-page wiki into an AI at once, the most relevant details can get lost. We need to break the text into smaller, focused pieces. This is chunking. We algorithmically split large documents into manageable segments, typically 256 to 512 tokens. To avoid cutting a sentence in half, we use a 50-token buffer. This overlap ensures adjacent chunks share enough information to preserve context. Chunk size is a balancing act. Chunks that are too small lack context, while chunks over 2,000 tokens often cover multiple topics, which makes it harder for the system to identify the most relevant information later. Proper chunking is the foundation of the pipeline. If these segments aren't self-contained and focused, the retrieval step will struggle to find the specific answers you need. Computers cannot search for meaning in raw text. To make our chunks searchable, we have to convert these words into a mathematical format that a computer can compare. We do this using an embedding function. For this build, we use TF-IDF. It calculates how often a word appears in a chunk and weights it against how rare that word is across all your documents. This process turns a text string like enterprise prorated refunds into an array of decimals. These numbers represent the statistical importance of each word within that specific chunk. By converting text into these numerical arrays, or vectors, we can mathematically measure how similar 2 pieces of text are. Chunks that share the same distinctive high-value words will produce vectors that are closer together in this mathematical space. This translation is what moves us beyond simple word matching. It allows the system to identify which documents are most relevant to a query based on the importance of the terms they contain. Now we move to the querying phase. When a user asks a question, the system must search through all our prepared chunks to find the one containing the answer. We take the user's question and run it through the exact same TF-IDF function we used for our documents. This gives us a new vector representing the user's inquiry. This graph plots chunks as points in space. To find the best match, we use cosine similarity. When the query vector drops in, the system measures the geometric angle against every document vector. The chunks with the narrowest angle are the most relevant. This pulls the specific paragraph about enterprise refunds, even if the user's question used slightly different phrasing. This geometric comparison is the engine of the search. It retrieves information based on the directional alignment of word importance, ensuring the most relevant context is prioritized for the final answer. Step 3 is augmentation. We now have 2 pieces of data, the user's original question and the specific paragraph we retrieved from our document store. We use a Python f-string to combine them. This creates a master prompt that includes both the retrieved context and the user's query in a single block of text. In this code block, we provide the AI with clear instructions. We tell it to answer the question using only the provided context. We then paste the retrieved chunk into the context variable and the user's question into the query variable. Finally, we send this entire block to the LLM. Because we provided the exact refund policy right in the prompt, the model can generate a factual response based on the actual company documentation. We have given a standard AI model access to localized knowledge from a private document store, and we achieved it without modifying the model's underlying weights. By linking these 4 steps together in Python, we have built a fully functional RAG pipeline. This shows the speed of the pipeline in practice. Data moves from raw documents through a mathematical filter into a focused answer in seconds. This architecture provides significant value for any organization. It creates an AI system that is easy to update, provides clear source attribution, and operates at a fraction of the cost of traditional fine-tuning. To move this toward a production-grade system, you can swap the TF-IDF code for a neural embedding API and integrate a dedicated vector database to manage millions of documents. The core logic remains the same. This retrieve and generate pattern is the standard for connecting large language models to the private, ever-changing data of the real world.